So let's recall some of the basics of regression. First, a regression equation again is used to predict a value called a dependent variable, which we'll denote as y, based on a number of independent variables, which we'll denote as x, or x1, x2, all the way to xn. Now the formula for a regression is the form of y hat equals beta 0 plus beta 1 x1 plus beta 2 x2 plus a series of beta n xn's with an error term. Please remember that the y hat is the predicted value. When we use the hat above a variable, it's usually denoting a predicted value or a prediction. Betas in the formula represent coefficients or multipliers of the independent variables. So these are the numbers that are going to represent a change in y based on a unit change in x. Epsilon in the equation represents error in the model, since no model is ever perfect. The standard error of the estimate is a metric that represents the approximate error of a general prediction. And finally, one of the statistical measures that we use is the adjusted R-squared, which represents the amount of variance in y explained by the regression model, and we use it as a means to determine how well the model performs. Once we have developed our regression model, our goal is the following: develop the most parsimonious model while ensuring the model meets all regression assumptions. So we're going to have a number of assumptions that we're going to focus on. They are that the mean of the residuals is 0. And that means that if we average out the errors, we should have a certain number above the line and a certain number below the line, being our positive and negative residuals. And the average of this will be 0. That these residuals are going to be normally distributed around the mean, so they're going to be bunched up near the regression line that we create. We're also going to show that the residuals will have a constant variance, or what's known as homoscedasticity. And this is basically going to show that the residuals will have no particular pattern. They will vary at a constant rate around this prediction line. And finally, that the residuals are independent from each other, which means that they are not correlated to a previous residual. And we're going to show in a separate video about these assumptions. We're also going to have to focus on the fact that a model is better than predicting, let's say, a straight average. And we'll have a way to compare multiple models using a test for overall fit or goodness of fit, using the F-test and an ANOVA table. We also want to have our coefficients in the model that are statistically significant. If there are no variables in the model that are statistically significant, we want to remove them and then rerun the model. And finally, that there exists low collinearity between independent variables. And what we mean by that is that the variables shouldn't be related to each other too much. And we're going to talk about this again in another module. So when we talk about a parsimonious model, and we've mentioned this before in a previous module, it's one in which we explain most of the variance with the fewest variables. And we're going to show how we can remove variables from the model. But let's just use the information that we have here. You're going to see here that we have an equation, y hat equals b0 plus b1 complaints plus b2 sales. And if we have both terms in the model, we have an adjusted R-squared of 0.82. Whereas if we have just complaints in the model, we have 0.80. And so what this basically tells us is that adding the sales variable adds about 2% explanatory power. Or in other words, an additional 2% of the variance in y is explained by adding sales to the model. So one might ask whether this is important at all. If we want to predict refunds, we may only want to focus on complaints and not sales. Now, some literature and some books may say, well, if you have a 1% increase or a 2% increase, you can keep them. And others might say you can ignore it if it's at 2% or 3%. And this is really up to the analyst or the statistician to take a look and see how important is that variable in explaining what's going on. But it's clear from this type of analysis that complaints is carrying most of the information and telling us about the variance in y. So complaints is the most important variable. So whether we keep sales or not, in reality, is going to come to the judgment of the analyst.